शिवम मैम वो सिस्टम ले लोगे आप? हाँ
वो भी चल रहा है।
हाँ सब चल रहा है। मैं सर बोला था तेरा 2 साल सीनियर हूँ मैं। अरे विशाल, ये जा क्यों नहीं रहा है नीचे? नीचे क्यों नहीं जा रही?
ये करना पड़ता है इसमें, शायद कुछ और ये पीपीटी नहीं है, लिब्रे ऑफिस का कुछ करा है। और यही कहना है। Spend more than
भैया भैया
That's it. Mm. So what are you doing today? What is the plan for today? Yeah. Okay. Right. Uh-huh. And are you going to do any application? Are you going to do this or what are you going to try on of these applications or I don't know, like what do you know, yeah, what you yeah, okay. Like you said. You could try to do that, and I guess that might be easy, but I don't know what they have yeah, what they have prepared for you. Not there yet. Yeah. Oh, so this is what it's okay. Let it run. So what are you doing then? Are you doing your own thing?
Actually, yesterday I did this. What was happening? The interface. It was not developing. It was
Uh-huh.
fast.
So for what application? What in a pipe laminar flow?
So in the beginning, it is a flat.
Mm-hmm.
So as
Yeah.
it goes through the pipe, it
Yeah,
should
yeah.
start developing, making it parabolic.
Parabolic, yeah. That's what you try to model, Yeah.
But it was not running.
Yeah.
I am thinking the boundary condition was probably under the yarn.
Okay.
So I'm going to the boundary.
You try, okay. So this is your single phase flow to try to make it run in a pipe.
Yes.
Yeah, yeah.
The same.
निकाल ही नहीं होगी।
Yeah.
Yesterday it was the like how to run it.
No. Did the others manage to do that, to run it properly or not?
No, people were able to run.
Okay, so but something happened to your simulation.
Theoretically, it should not come flat. It should come to some extent,
Yeah.
not completely, but at least there should be some parabolic at the
That's right. Yeah.
So I'm thinking
Yeah,
Here we have
yeah.
boundary condition.
Okay, so you were not all given the same boundary conditions? Did you have to decide or did you change them yourself?
So usually everything was given.
Mhm.
You just have to run.
Okay,
Now I'm trying to change, thinking. is
Okay.
different. I'm just trying to run.
to sit around it, yeah. Okay, good luck. So did the others manage to make it run parabolic?
No.
No, right, okay.
Those are same everywhere.
Yeah. It was the same problem, okay,
So
Yeah.
the key probably the meshing is very in the source.
okay.
But my understanding, the meshing is small enough
Yeah,
to have that thing.
so it might be the boundaries.
So might be the boundary condition because the it's like flux flow is moving.
So do you have like, no, I don't know how you do the walls, like snow slip walls or?
Okay.
Right.
Let it flow.
Mhm.
When we define pressure, then the velocity gradients are considered to be zero.
Hmm,
When you define pressure, so
Yeah.
pressure is defined at the outlet,
Yeah,
but this velocity we are defining uniform 0, 0, 0.
huh,
0, 0 means it is this.
yeah. At the exit,
So what I am
Yeah.
thinking because of this,
maybe it
default
makes
is
all the. Mm. So everything is zero rather than, yeah, I see what you mean. Yeah, okay, yeah. So you can still have pressure. Do you have pressure boundary? Yeah, pressure inlet, outlet velocity, yeah?
pressure is there.
Yeah.
Pressure is defined separate.
Yeah,
Inlet flux is there.
Yeah.
Just like this flux.
Yeah.
We are not defining any pressure.
okay,
It will automatically calculate.
Okay.
Here we are defining outlet pressure at 0
Mhm.
and at the pipe wall, flux is 0.
Yeah, okay.
So that means we are not.
Yeah.
It should be 0 at outlet.
At the outlet, exactly. Yeah.
What
Yeah.
has been done here?
But maybe it's this, what is this? Yeah.
Velocity. They define the velocity and that.
Then they
Make
set
the
it
unit
zero. Yeah.
So that.
So
part-
can you just delete that or,
So I'm
this is the
saying
initial condition, no? Because, yeah,
initial and boundary condition.
bounded. Okay, yeah.
So I'm trying to see if it is it will run or not, or some.
Okay.
And will it result in a different?
Yeah, okay, that's a good effort. Yeah. Good luck.
Thanks.
Because this is different to what you run, isn't it? The kind of the way you set the,
Yeah.
and then, yeah, slightly different the language, I mean, the way you set the.
Yeah.
Yeah. Okay, yeah, keep going. Yeah. Hi, how are you doing here? Oh, blank screen. Everything is finished.
On other slides.
Ah, you've done all the slide, okay. Yeah. Are you going to do any, I'll ask them. So where are you now? What, do you have to run any simulation? Is the idea to run any two-phase simulation?
Yeah,
Yeah, okay,
here actually full file is not this thing. So
okay.
we managed
So
to
just
test
get
the-
him to, yeah. How did it go yesterday? Was it good or with the tutorial? Um,
So we are facing difficulties. First time I
Okay, yeah.
OpenFlow, but
Yeah.
console I know a little bit, but
Okay, right,
so
okay.
this flow I did some similar, but OpenFlow new interface.
It's a very new, yeah.
Okay.
So the same with you, you have you worked with simulation? Yeah, or now what in Fluent, yeah.
Actually, I'm asking you, yesterday some lecture when you were teaching like small channel design.
Mhm.
In the small channel, how much small means how to ensure that that much small is we give the exact result or whatever we want to generate the drop safe or
What do you mean? How small it can be, or
how small it is.
I think it is a bit subjective, but you can look at what we said in the first lecture where we set the bond number.
Right.
Yeah, and the other thing is to see, of course, if you have any effect of gravity. So if you have like a pattern that's supposed to be symmetric, like Taylor flow, annular flow, and you see that the one side is it's like sitting down. If you have a Taylor flow, plug flow, if the plug is closer to the bottom wall, it means you have some gravity. Yeah. So that's it, like your visual, let's say, check. But if you check the bond number then this is the theoretical way of doing it.
If the size is in micron or some few
For
micron,
my microns, definitely, yeah,
then
yeah.
the physics
So,
will change. So it
I mean, if you go, yeah, I mean, it depends on how small you go. Because then there is, we didn't talk about the other extreme, but I think it, so in the very beginning, when people were using a lot of gas phase systems, they were having this Knudsen number. I mean, if you look at the literature, that basically if you go very small, I can't remember the number, then you don't talk about a continuum anymore because you have the individual gas molecules.
Right.
Okay, but this is actually quite small
Yeah,
channels,
that's,
maybe low pressure, as well. So,
I don't know.
but I don't know. I mean, if the application you have is along these lines, then have a look. And then there is this Knudsen number
That's
that
it,
is,
yeah.
that kind of gives you, yeah, it was a small value, but basically you have to be very small channels, like not even a micron is okay. I think even smaller, or low pressure. So basically, you compare is the discussion whether you have a continuum, fluid as a continuum, or fluid as discrete molecule. Yeah. It's that's when you cannot use anything from what we said because it's different.
Like whatever the next now, one thing I might see now. Our lab we are doing bit by books, bit by books, where we do micro chess.
Could
Bit
be,
by books,
yeah.
we make very mobile also. How
Mhm.
much bit we can enhance very
Yeah, we check the numbers because these give you a good idea.
okay.
I don't think heat pipes would be a problem, to be honest. But again, I don't know how small you go. What's your, I mean, a bigger, higher pressure helps because, of course, your gas becomes more dense.
Right, right.
Yeah, with liquids, you really have to go down to molecular scales to have any problems. But with gases, especially if the pressure is low, sometimes people were worried if the pressure drop is very high, you start with a high pressure, then becomes very, but I think these are, it depends on your system, but you really have to have low pressures and very small channels, like smaller than atmospheric low pressures.
Right.
Yeah.
Yeah. We are trying to do like we doing this bit by work.
Yeah, what's your channels?
Yeah.
How big are these?
It's 0.4%. It's 0.5. We're trying 0.5 the diameter.
0.5 what?
Amen.
500 microns. No, I mean, yeah, unless you are very, 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 very low pressure. 500 microns is okay, but I mean, do check the numbers. It's all dimensionless numbers. And it depends on the type of gas, because it's the density,
Microgel or something like hydrogen, not hydrogen, but microgel or this thing. It may help to change the phase change phenomena like from the liquid to gas phase. Is this help? It may help or not.
well, I don't know what you mean, like to have evaporation.
Some part of the evaporator and some part is condenser also. In the heat pipe, is generally
Yeah,
process.
but this is a surfactants. I don't know, do you need to add these things in your case? I mean, why would you add the microgels or anything?
Means whatever the dimension can maximize, minimize the dimension size like 500 micron. Further, we would enhance the fluid behavior or pulsating this Taylor flow, bubble.
Yeah, with evaporation. This, I mean, I don't know, I don't know that well this literature on evaporation. We do some evaporation, but on fundamentals, not on heat pipes. So, I think about one thing to, yeah.
There is evaporation and condensation.
Uh,
Same.
no, not in your body. Hopefully not.
No, I mean,
Yeah,
sweat, how it's.
I'm sweating, but you
Uh,
don't evaporate in your body.
Actually, not
Yeah.
evaporation.
Yeah,
just
yeah,
in the,
yeah, yeah.
uh,
But I think, I mean, I think, but there, what people might have done is improve the mixing. So all these mixes were showing in the first lecture where you have the like herring bones and because I think what you need is better. It depends on which part you try to improve. Okay, if it's evaporation means that you want to, you have to create some sort of, yeah, the mixing helps because then of course your fluids and your heat transfers better. So there is a lot of the surface to be, to have some structure on the surface. So people have used these herringbones or other ideas.
That is good. Idea.
The other thing is basically in all these cases you want to enhance the heat transfer, isn't it?
Right.
Yeah, so it might be again whether your configuration is can you do channels or can you do plates? Because I think there had been work where people look at the very thin plates as well, not a channel, but one dimension is very thin, but like a plate, like a LSO cell. Yeah,
Right.
I think that because it has a lot of heat transfer, so one dimension, the heat transfer dimension becomes very thin.
Okay.
But you have a lot of area because you have a plate rather than a channel. Yeah. So I think, and then you can do some structuring, but it depends on what you want to do. I don't think these particles, I don't think they would help because these are like surfactants. Again, so you want something to make,
Not like whatever finished. I
okay,
then
all right, okay, okay.
some your CTAP, DTAP, all this affected.
Where
1,000 literature or whatever.
to do what?
To enhancing the actually capturing the more and more of the surface.
Might change the wettability of the surface.
Right.
Yeah. Maybe they change because once you add surfactants, you affect the. Yeah, I don't think it evaporation is interesting because we do a bit of work there and it's not very clear what it does, but it may change the contact angle.
No, it's transparent. They change the configuration.
Right. So what affects to miniaturize the channel diameter from 1 mm to
Yeah.
0.5. So what
Yeah.
effect for the
With the heat, I mean, nothing much unless that's what I'm saying. If you go down, the general laws should apply. Yeah, if you have continuum, then you just think the general laws. So if you minimize the heat transfer distance, let's say, then heat transfer should be faster.
Right.
So what I was saying is that unless you go to cases where you really are very low pressures, very very small, but I don't think 0.5 millimeter is small enough. It's smaller. Then it's all continuum. So there's not new phenomena. It's just that you see different sides of the phenomena. But so the mixing should help because heat transfer happens this way. You just have to make sure that it's all by diffusion. So you have to make sure that there's very you have still your boundary layer, laminar flow. You have to make sure it goes fast. So I think if you have a lot of irregularities, you help that like roughness.
That we try to.
Yeah. The other is the wettability of the surface, and maybe that's where you like to play. So because if you have a condensation, evaporation, you want to have actually roughness may help in evaporation because you have nucleation and then or even the surface property like wettability may affect evaporation. Condensation might be the opposite in a way. So I think it's more like surface properties than
Which surface property is actually enhancing the heat transfer rate and further the
Yeah.
rate, increase the
if you have phenomena
right.
like the individual phenomena.
Recently some literature they're suggesting like wettability there, whatever the like sometimes they are suggesting hydrophobicity. Sometimes in recent literature it's just opposite. They are telling more and more hydrophilic, it will give the more and more enhancement of the heat transfer. Like this.
I think you need to look at the phenomena because I don't think I cannot generalize and that's something you can. You really need to see the fundamentals are important because if you have a liquid, your heat transfer from the wall will be faster.
Right.
Yeah. If you have a gas, then your heat transfer will be reduced.
Okay.
Yeah, of course, gas heat transfer is faster in liquids than in gases. So it depends on what you're trying to improve. I'm not. I don't think there is. You can go one way. I think the overall the empirical observation might be this, but if you try to work in that area, I think you need to see what am I trying to improve because if you have heat device evaporation and then condensation. You might even have different properties, because like two opposite phenomena. What helps evaporation? To start, do you evaporate from the surface or do you boil? I mean, I don't know what happens.
Boil,
It's boiling,
just
yeah.
starting of the boiling, it's.
So you need to
Yeah.
encourage nucleation, yeah.
Right, right.
What causes condensation? It helps more than if you have hydrophobic.
Okay.
Do you see? Yeah, when actually in condensation, sometimes if the surface is hydrophilic, phobic, you don't form a film, you form drops.
Right.
So which one is better? You know, I think I don't think there is you can say hydrophilic works overall better.
Okay.
It's this, what does it do in the different steps? Roughness helps evaporation.
Right.
When you have condensation, what do you want? Do you want the film or do you want drops? Drops means faster
Faster, heat transfer.
heat transfer. Yeah, so maybe they're actually not hydrophilic, but hydrophobic surface is better. With evaporation, I don't know if hydrophilic or hydrophobic plays a role.
Okay.
We don't know what helps nucleation. Roughness helps nucleation. I don't know what helps the.
Sometimes they're doing
So-
some structure or something like.
Yeah, exactly. Yeah, like a very, yeah, which you can do, or general roughness.
Like now. it's-
So, Yeah, it's like pin.
Yeah.
Mm, yeah. But I think, I mean, I don't know what you're trying to do, but I think it's like the different steps. And again, to check in the literature that you have been reading. I mean, it might be an overall outcome that the hydrophilicity helps, but why? I think it's the why you might want to dig a bit more. I mean, as a reviewer, if you submit a paper, I will say, why does that happen? Okay.
Yeah, right, right.
So it's good to
Sometimes-
take on the phenomena yeah. It might be two different phenomena. Maybe it's competing phenomena. Maybe it's not. I cannot. I mean, I don't know the whole process correctly. Could be that, yeah, generally having hydrophilic walls helps or hydrophobic in that sense because evaporation is condensation, heat transfer is faster. If you have a hydrophobic walls, is the evaporation faster? I don't know. Might be. Might be. So maybe having hydrophobic walls in general helps. Yeah.
Right, right. Most
But,
of the
yeah.
literature are there, but still some recent literature, what we are suggesting, more and more philic, which giving the more and more condensation.
So more and more
Phobicity.
for this.
Ah.
Yeah, maybe that's that. If you have very hydrophobic channels, of course, then it's much more difficult to fill them. If you think, yeah, okay, if you start with water, yeah, because especially if they're very small, it can be a challenge to push the air out to fill them with water.
Okay, okay.
But yeah, yeah. But I think it's looking at the phenomena because there is explanations. But I think it's all. I don't think like going into atomic level is relevant. But maybe it's the gotability or the. But it's going down to the phenomena, isn't it? It's like nucleation, rates of heat transfer, and this is actually from large, even large channels. It's the same thing. Yeah. Yeah.
Difficult to handle also.
Yeah.
During the food process, it's
Yeah.
handling the food
Mhm.
plant or something, it's
Mhm.
really difficult.
Yeah.
Not like, I'm not telling about any other lab on cheap work or
Mhm.
what we can do in the proper room temperature. Yes, we are having all this facility micro.
Yeah. How high you go in temperature? Do you go to how high temperatures do you have?
Generally, between 90 different.
90, yeah. So you get evaporation, yeah. Good, yeah. Now we have to do the tutorial.
Yeah. Okay, thank you.
Is that still running? Okay. Have to see your results in the end. Wow. Yeah.